Right, welcome to this instalment. This is the last instalment, I would say, of, well, it actually is, of AQA AS quantum phenomena within Unit 1. Now, we're going to be looking at wave-particle duality today. Now, what you may be asking me the first question, what is wave-particle duality? Well, it's quite simple. Well, it's not simple, but it's a lot simpler than it sounds. Wave-particle duality sounds a bit fancy to me. I'm just going to dumb it down, because I haven't got it done, to particle waves, or particle plus waves. This basically means particles can be waves and yeah, so so light can be particles and waves. I just put light as a thing to them. There are many experiments where light has been proven to act like waves and light to act like particles. Let me just see if it's got any examples in here. So I'm just going through the book and I'm making sure if there's any examples, I'll let you know. I've gone over it. I'm just making sure I've not missed anything. So obviously light we can show with the photoelectric effect. Obviously there's a wave in the particle. So all you need to know really, there's no real examples in there worthwhile. So you just need to know that light acts like a particle and acts like a wave. And now because a wave acts like a particle and acts like a wave, we can derive this formula of lambda equals sorry, is that the right way around? Yeah, equals h over p. And you may be asking me, well, we know lambda, because that's wavelength. What I'm going to do is actually rewrite this equation out for you in English. Wavelength. You go, well, what's h? Well, h is Planck's constant, which we should know from photons, which I haven't put up on YouTube yet, but we'll get round to it soon enough. So Planck's constant over p is the momentum, which you should know from GCSE studies. Now we can simplify momentum. Well, we can't. Well, actually, it's not simplifying it per se, but it's just explaining it. So, as momentum p equals mass times velocity, we can just put that into the equation equals h over mv, which is exactly the same as saying that. So that is the broadly. I can't say it right. That one. I don't know if you can read it. Yeah. You probably can't, but it's called de Broglie. He was a French physicist. Anyway, so momentum is measured in kilograms per second. H is Planck's constant. Lambda is the wavelength of a particle. Velocity is in meters per second. So if we increase a particle's momentum, sorry, I was just checking something there. If we increase particle's momentum, so an increase mv, we, as you can tell by the equation, if we increase mv, we're going to decrease the wavelength. Just from, if we put a higher number in here and keep this number the same, we're going to decrease this number. Sorry, just put that. So if we decrease lambda, we decrease the wavelength. That's just one sort of thing you need to know. Don't know if you. Just going to check if you can still see that actually. Just give me a minute. Yeah, looks like you can. So that's the main thing there. Damn it, it's gone back. So I'm just making sure I've not missed anything. Just give us a minute. Symbols as part of light diffraction, measurements for wavelengths, similar magnitude to heat. So, as we know, is this what it's talking about? So, as we know, when we try and determine the wavelength of light, we can use Young's double slits. So I'll just draw this and I'll move out of the way. I've got a thing here. Fringes. Sorry, that's a very poor attempt at Young's modulus. Young's fringes even, which is covered in Unit 2, but we went over it. So that is, we use Young's double slit to measure the exact wavelength of light. Even though it's not brilliant, we can use diffraction grating as a bit more of an interesting way of working it out. So, to work out the wavelength of light of all particles, or light, which is exactly what we're talking about, and light's what we're talking about, we can just use Young's double slit. And obviously, as particle waves, yeah, so if we put electrons through there, we could measure the wavelength of an electron, for example. We could just put it into Broglie's formula, and just use that to put in. Now I'm going to do some questions, seeing as we've got a bit of time here. So I'm going to move out of the way, let you copy that down if you haven't done so already, and move out of the way. Just give you a minute to copy that down. If you don't mind, I'll just shoot ahead and we'll get on with this. Cool. Hopefully you've understand. You just need to know that formula. I mean, it is given to you in the exam, so you don't need to worry about remembering that. But if you're the certain person that likes to remember where it came from, that's just, I don't really want to waste your time with that. You're just mixing the two formulas for wavelength of light and wavelength of wave, even if that makes any sense at all to anyone. Hopefully it does. Otherwise you just need to remember that formula. So the formula is y equals p, or Planck's, h, Planck's constant over mv, or p. Just put all p. That's a bit confusing. I'll just leave mv on the bottom. Actually, it's a bit confusing that, if we're honest. So wave particle duality. So we've explained it. We've gone through it. Now I'm going to go through a few examples. Now the question here. Actually, trying to pick a better one. That was quite a poor one. Actually, poor choice from me. It says calculate the wavelength. So it wants us to calculate the wavelength. So we're not going to know that. I'm just going to explain it, put down what we know. So the wavelength of the following, the speed of light. Yeah, so it's not asking for the speed of light, a wavelength, the speed of light, but it tells you the speed, which is speed of light, which is even more confusing than it could be. It could have said anything else. Meters per second. The mass of the electron, 9.1 times 10 to the minus 31. Oh, sorry, yeah. Oh, if I before said it's 1.67 times 10 to the minus 27, I've messed that up. So that's the mass of an electron. and a Planck's constant. You're given that in the exam, so I messed it up. You're probably not going to, but you're given it in the exam. 6.6 times 10 to the minus 34 joules per second. So that's what we're given. It says an electron moving at 1/10 the speed, so times 0.1, because it's a tenth, so it times it by 0.1. And let me get my good old calculator out. See, this is what a real man has, this calculator. Ow. Real man, yeah. And I've just stabbed myself with a protractor, never mind. So, 3 times 10 to the 8, let me just do this. Oh, God's sake. Yeah, 3 times, sorry, just give me a minute. 10 to the 8 times 0. Oh, it's a bit hard using this calculator, you know, it's a bit crazy, too manly. And it's just 3 times 10 to the 7. Sorry, I should know that, but I was just making sure. 3 times 10 to the 7. That should be a power. First of all, 10 to the 7. So that's your wave. Sorry, just sorry about that. You know, with me being so popular, I get people knocking on my door saying, "Can you help us with this physics?" Happens all the time. So where were we? Yeah. So we were. This was the question being asked. So there are what we've been given, and it says find the equivalent wavelength. We know. We just put. We've got everything here we need to know. We can just put. Oh, that's the same V actually. So we just put all the standard things into the wavelength. So 6.6 times 10 to the minus 34 over mass times velocity, which is 9.1 times 10, so minus 31 times. Sorry, this looks a bit scruffy. Times the velocity, which is 3 times 10 to the 7. And sorry, let me just work that out and see what you can do that and see what you get. If it's the same as what I get, then lovely jubbly. Yep, I got the wavelength as 2.4 times 10 to the minus 11 meters. Obviously convert it to nanometers, but it's best you just leave it as meters, because that's the SI unit. Now, hopefully that's just a small introduction. That's just, obviously you're going to get harder questions than that, but I just wanted to introduce you to a question, obviously not waste much of your time. So we'll see you in the next video.